Welcome to this explainer. Look, if you're a B.Tech computer science student, you already know there are these massive foundational concepts you just absolutely have to master. And today, we're diving deep into topic 1.13 of your computer network syllabus to unravel the absolute genius of Ethernet standards and frame formats. Let's just jump right in, because honestly, understanding how data physically moves across a wire is essentially understanding the heartbeat of the entire modern internet. We're going to break down all these highly technical specs into a super clear, easy-to-follow journey.
To start us off, I want you to think about the real-world mystery of global trade. I mean, how are millions of physical items, cars, electronics, literally tons of bananas, shipped worldwide across oceans, trains, and trucks, without just complete and utter confusion? Well, the answer is the standardized physical shipping container. Now, the digital world had to invent its very own version of that universal box to prevent your streaming videos, text messages, or those massive software updates from just breaking into pure digital chaos.
Section 1. Discovering IEEE 802.3, the standard that calmed the chaos. So the secret to this flawless global movement, whether we're talking physical cargo or our digital networks, comes down to a universally agreed-upon standard. We need rules, right? We need a highly specific blueprint that every single computer, switch, and router on the planet agrees to follow without question.
And for our wired networks, that mastermind standard is called IEEE 802.3. You're going to see this everywhere in your networking textbooks. It's the overarching rulebook that dictates exactly how data must be packaged and handled to avoid network collisions on an Ethernet connection. Specifically, it governs the physical layer and the data link layer's media access control, or MAC. Without this strict standard in place, computers would literally just be shouting digital noise at each other over the wires. It'd be a chaotic mess of colliding data. Think of it like a truly terrible group video call where everyone tries to talk at the exact same time.
Okay, moving to Section 2. Inside the digital container, the anatomy of an Ethernet frame. Let's pry open this universal digital shipping container, which in computer science we call an Ethernet frame, and examine its anatomy from top to bottom. Think of this as dissecting the exact blueprint that IEEE 802.3 demands for every single piece of data traveling over a cable.
Every single frame built under this standard follows exact sequential steps to ensure the data gets precisely where it needs to go. It's this beautifully structured 5-step architecture. We start with a preamble and SFD, move on to the MAC addresses, then the type or length, followed by the payload, and wrap it all up with the FCS. Let's break down how this builds, step by step.
Step 1. First up, the preamble and start frame delimiter, or SFD. These act like a flashing warning siren. You see, when a receiver is just sitting idle, it needs a heads up that data is actually coming so it can prepare to read the incoming bits perfectly. This sequence tells the receiving computer, hey, a new frame is arriving, and it physically syncs up their internal clocks. It's basically the network's way of saying, attention, get ready, incoming data starting right now.
Next up, we have the MAC addresses. Now, the crucial thing to understand here is that these represent the exact physical hardware locations of where the data is coming from, the source, and where it's going, the destination. Every single network interface card has a truly unique MAC address, permanently burned right into it. By putting the destination MAC address right at the very front of the frame, network switches can instantly look at it and route the container down the correct physical wire without having to open it up and snoop through the contents.
On to Step 3. Then, the type or length field tells the network exactly what kind of protocol is hiding inside this container. Is the cargo inside an IPv4 packet? Is it IPv6? Or is it something else entirely? This field acts just like a shipping manifest glued to the outside of the box, letting the receiving computer know exactly which software process should handle the data once the container is finally opened.
Step 4 is the payload, which, let's be real, is arguably the most important part, because it holds the actual cargo. This is the whole reason the frame exists in the first place. It contains the text of an email, a chunk of a streaming video, or a piece of that new game you're downloading. Under the standard, this payload must be at least 46 bytes long, and it maxes out at exactly 1,500 bytes.
Finally, Step 5. The frame check sequence, or FCS, runs a cyclic redundancy check, usually just called a CRC. This acts as a digital security checkpoint. Before the sender ships the frame, it does some complex math on the frame's contents and stores the answer right in the FCS. When the receiver gets the frame, it does the exact same math. If the answers match, awesome, the data is safe. But if they don't, it absolutely guarantees the cargo was corrupted by electrical interference during transit and, well, the frame is immediately thrown away.
Section 3. Shipping containers of data,
physical world versus digital world. Now, let's really lock this concept into your memory by directly mapping the Ethernet frame to our real-world physical shipping container analogy. Honestly, this is the absolute best way to visualize how these abstract concepts function as real, tangible systems.
This just brilliantly illustrates the connection. Just like a physical container has a standard steel size, our Ethernet frame has a strict max 1500 byte payload limit. The physical to and from shipping labels, those are exactly what your MAC addresses do. Your physical cargo is your data payload. And that heavy-duty security padlock on the container doors? Yep, that is your FCS with its CRC check, making sure absolutely no one messed with your stuff along the way.
Section 4. Ethernet in the real world, the massive scale of data transfer. Understanding this structure is so crucial because it helps us grasp the sheer, mind-blowing scale at which Ethernet operates in the real world, every single second. I mean, it's one thing to talk about a single frame. It's another to think about how these frames power your daily life.
Because the standard data payload is typically capped at just 1,500 bytes, a single high-definition video requires literally millions of these identical digital shipping containers to be processed flawlessly. Just think about that for a second. Every time you watch a movie, millions of frames are being built with preambles, stamped with MAC addresses, filled with 1,500 bytes of video payload, locked with an FCS, and fired across wires at the speed of light, all without a single collision. That is the magic of IEEE 802.3.
Section 5. The ultimate takeaway. A quick exam recap. We've unpacked a ton of technical details for topic 1.13, so let's do a rapid-fire recap of what you need to master. As a computer science student, you really need to be able to recall these layers instantly.
Add this to your mental checklist right now, okay? The standard is IEEE 802.3. That sets the rules. The sync is handled by the preamble and SFD, waking up the receiver. Routing is dictated by those physical MAC addresses. The cargo is the payload, capped at 1,500 bytes. And finally, the error check is the FCS, using CRC math to catch any electrical corruption.
To wrap up this explainer, if you remember only one thing, remember this. The Ethernet frame is the universal digital shipping container, preventing the modern internet from collapsing into absolute chaos. But hey, here is something to think about before your next class. If our digital containers max out at 1,500 bytes, how on earth do networks handle the massive 4K virtual reality streams of the future? Do we build bigger containers, or do we just ship them faster? Thanks so much for learning with me today, and keep that curiosity sharp.